Okay, so you guys are now being recorded. Okay, and now what I'm going to do, and Thomas, I'm talking to everyone, but I'm really talking to you more than others. I'm going to share some content. Okay, and I'm going to share my application screen. And I'm going to go to here. And Thomas, what you should be seeing is an unquiz.
Yeah, I can see it.
Excellent, that is good, and I'm going to assume that that means other people can see it too. Now, I want to frame this because these unquizzes are not threatening things at all. This is a problem where it's a good opportunity. You see, it has all the benefits of having a quiz with none of the downsides. And so what happens is, here's a problem that I could have asked you. It's based on what we learned last time. And I'm going to encourage everybody to try to do it. Now, I realize that I can't police this. Some of you will perhaps play with your cell phones and just wait. But I will tell you that there is genuine pedagogical value in you trying this. And so this would be a problem that I would be in a high stakes assessment. This would be with no calculators. Now, the reason this is I'm trying to think of the right words here, is not threatening is because you will grade this yourself, okay? And in fact, it will be something that you will hold close. So you see, Thomas, as an example, I will not know if you get this perfectly right or if you get this totally wrong, okay? But you will know, and that's the important thing, okay? And this is based on what we did last time. So what I'm going to do, and by the way, one of the things that is difficult for me, and actually I've got to tell you it's difficult for others like Jesse Hayes Carver even. I sometimes have asked Jesse Hayes Carver, I've given him a draft of the test, and I say, how long do you think this will take? And Jesse Hayes Carver is a very capable fellow, and he said, well, that would take me a half an hour. Well, you see, Jesse Hayes Carver is not a good estimate of how long something will take. So I don't know if I'm giving you enough time to do this or not. I'm kind of watching my clock. It's 8:02. So we're going to launch this. I'm going to read it. I'm going to give you 5 minutes to do the problem. That might not be enough, and you might say, oh, you're being mean to me. No, I'm not. I'm just trying to move things along. So I'm going to read this, and everybody work on this for 5 minutes. So I'll start the clock after I read this. Okay. So, and this is exactly what I would do, and the directions will be, don't use calculators. You sketch the graph, you do the calculations by hand, because that's how you have to do it on the high stakes assessment. Okay, so here we go then. So I'm reading it. Determine the area of the region bounded by y equal 8 over x, y equal 2x, and x equal 4. Okay, and I think I said I'd give you 5 minutes. I think I will give you 7 minutes. So at 8:10, I will come back, and what we will do is we will talk through a solution to this, and will be grading your own papers. Okay, so everybody have a go again. There's no pressure, there's no anxiety with this. It's just seeing where you are. Thomas, you good with me?
Yep, all good.
Good, okay. Let's everybody give it a go, please. Thomas, can you hear me?
Yep.
Okay, excellent. We're going to, and I'm not just talking to Thomas, but he's kind of my, oh, he's agreed to be my deputy here, which is useful. So we're going to declare this quiz over. So if you solved it, congratulations. If not, you have an opportunity to learn something. So what I'm going to do is we're going to go through a solution to this, and you're grading your own paper. I'll talk about how I might grade it, so you get a sense of that. But again, this is just you figuring out where are you in the course. Okay, so let me go then to the, I'm going to start the solution. So these things usually start with you sketching a graph of things. And Thomas, I'm hoping you can see my cursor wiggling about here.
Yep.
Excellent. So this, so far things are working. That's great. Okay, so this red graph is a graph of y equal 8 over x. And so that curve kind of looks like this. The graph of y equal 2x is going to be a line. It's shown blue here. So that's what y equal 2x is. And then there was a third function there, I guess. Actually, it's not a function because it's not single value, but there were a third thing to graph, I guess. It was called x equal 4. So you see x equal 4 is a vertical line. So that's this black business here. So you see your job then is to find out what is this green area. Okay, so and we learned formulas and things like that. So we know it's going to be the function that is on top minus the function that's on the bottom. So that is the blue minus the red. But then I have to find the what do I want to call it? The limits of the integral. Okay, and one of the limits is clearly going to be x equal 4, and the other limit is going to be this thing that we have to find, this point of intersection here. Now, I am going to tell you that, and again, I'm leading into something we're going to be discussing today. That's another reason for these unquizzes. I talked about, you could draw slices, either vertical or horizontal. Now I'm going to tell you that here, drawing the horizontal slices would be bad. I mean, again, you could do the problem that way. That doesn't mean it's impossible. But if you're drawing the horizontal slices, you see you change because you're drawing the horizontal slices. I'm wiggling this horizontally now. So if you're drawing the horizontal slices, the curve that's on top is this x equal 4, and the one that's on bottom is this y equal 8 over x for a while. So that's what's happening here. But then it changes at this point. And from here on, the curve that is on, I shouldn't say on top, but has higher values is x equal 4. And the one that has lower values is y equal 2x. And you would be doing dy, and you would have to do two integrals. So a much better approach, because I didn't tell you a certain way to do it, is to draw the slices this way, vertically, and that means that we're going to be integrating dx. And the nice thing about that is, if we're integrating dx, in the area that we're trying to find, the blue curve is always on top of the red curve. We only have one integral to do rather than two integrals to do. So the first step is going to be graphing this, and if there were a 10-point problem, I might give you some credit for graphing it and kind of say, oh, that's the area I'm trying to find. But now we have to use our formula. So I'm going to go into a calculation now. And the first thing that we need to do is determine the point of intersection. So I say, well, where do those two curves overlap? And so you say, well, 8 over x has to be equal to 2 over x. So then what I'm going to do is multiply both sides by x and solve this, and I will get that this intersects when x squared is equal to 4. You see, if I do that, both sides by x, the x goes away here, I would have 8, and I'll have 2x squared equals 8, but then divide both sides by the 2. So x squared equals 4, so x is equal to minus 2 and plus 2. But now you see, when we look at the picture, even though there are two places where those curves do intersect, the negative value is not in play for this one because of the picture that we drew. And so the limits on x then are from 2 to 4. Okay, so we're going to say the area that we desire is going from 2 to 4. And then there's the top curve, which was the 2x, minus the bottom curve, which is 8 over x dx. So now we have to do the integral because we have to finish the calculation. And okay, so all right, so when you integrate this, the 2, you could pull through the integral, and you have x to the 1, so you add 1 to the exponent, divide by the new exponent. So it's going to be x squared over 2, but the 2's are going to whack with one another, cancel rather. I should not say whack. That is bad terminology. I have better vocabulary than that. So this is x squared for that first integral. This minus sign is that minus sign. Then I have to integrate 8 over x. Now I can pull the 8 through the integral again, and I'm integrating 1 over x dx. Now, this is one of the integrals you're supposed to know. This is the natural logarithm of the absolute value of x. And then the fundamental theorem of calculus says we evaluate this and we plug in the top integral and we plug in the bottom integral, and we do that. And your answer then, and this is the exact answer, is 12 minus 8 natural logarithm of 4 plus 8 natural logarithm of 2. Now you actually could do some clever logarithm things with this too if you wanted to. I'm not doing that right now. And by the way, this notes I'm kind of pretending like I'm an engineer, and I say, oh, I'll plug that in a calculator. You won't plug that into a calculator. You'll give me an answer that is like this. Now, there are different ways that you could write this because you see you got the sum or difference of logs, and you can use properties of logs. So do rest assured that whenever I grade this, I will look at your answer, and I will work to discern that you're, that you've come up with the right kind of answer. I will check that carefully. So full credit is here. So if you got this completely right, congratulations. If not, maybe you learned something. And I am going to pause now for questions. Now, given the number of screens that I have open and stuff like that, I'm going to ask that you perhaps go off mic with your questions, and I will, count to 10 Mississippi, and so people can certainly ask you questions, but I'm really going to ask you to, try to go on audio and shout out. And I do want to deal with any questions that you all might have before we go on. So I'm starting my count now. And Thomas, you're still with me?
Yeah, I'm still here.
Okay, so I am going to, in my head, not aloud, I'm going to count to 10 Mississippi, but somebody, if you got questions, just jump in.
How are we gonna turn this in?
You aren't turning it in, but I'm giving you credit for doing it.
Oh, okay.
And
Thank you.
you might not realize it, but gee, I'm being very kind to you. See, what I want you to do is I want you to get the benefits of actually having a quiz problem, because this is a kind of question that I could ask. You got the benefit of doing it. And what that tells you is, gee, where are you in the course? And if you got the correct answer, you should probably say, yeah, I'm in pretty good shape in the course. If you didn't get the correct answer, you might say, I might not be where I want to be in this course. Now, I know it's only day 2, but we're going to move pretty fast. So, that's giving you information. I also was giving you little bits of clues about, things that might be worth partial credit. For example, the correct graph would be probably worth something, and finding the points of intersection would be worth something. And you really do, to get full credit, you would get this. And I've got to tell you, on this problem, what I would probably say is you probably get 5, if it was worth 10 points, you might get 5 points partial credit if you did something right. But then the thing that gives you full credit is, an actual correct answer, and that would be worth 10 points. Okay, so I did answer one question, and by the way, I've told you guys, and this is what I try to do in these VCMs, and again, this is not perfect, I know, but I'm going to start the count again to 10 in case some other people have some questions about this.
So I guess I'm curious, let's say we're working out this problem on a test or on whatever assessment, and
I know I'm interrupting you, but I think your question is really about a high stakes assessment. Yes.
yeah. So let's say we're working out this problem on an assessment, and like we make a mistake, we put the wrong scale on the graph or something, but we ended up with the right answer at the end. Is the right answer going to trump the mistake we made along the way? Does that make sense?
I guess I'm going to say I'm all about the right answer, but realize that you don't have a calculator to do numerical integration by plugging it into your calculator, because there are not calculators on high stakes assessments. And that's not my idea. That's really the math department's idea. That's what I'm supposed to be doing. So that's what I will do. Did I answer your question? I hope.
Yeah. I can just definitely see myself making a silly mistake, like just putting it in the wrong quadrant, just doing something silly that like ends up ironing out in the end. You know what I mean? And so that's why I was wondering.
Got to tell you, I am rarely that lucky, but you might be. Okay, and luck is not a bad thing. And I got to tell you, when I'm grading this, I'm going to glance at the answer, and if the answer is right, I will move on. Okay, I'm starting my count again. Okay, Thomas, I hit 10 Mississippi, so I'm going to pretend that everybody is good with this. So, there it is. And what you should do is say, okay, where am I with respect to this? Did I get all this right? And if you got all this right, you might say, oh, yeah, I am in pretty good shape. If you didn't get it all right, you say, oh, I have some work to do, and then you start doing the work. Okay, so that is good, and thank you for all of that. Now, oops, I'm going back to something else now. Now I'm going to go back to the general thing. Now the unquiz has already been done, but I've got some opening remarks, I guess. And the first thing I always do, or I shouldn't say always, but what I really try to do is I open the floor for questions that people may want to ask. Now, I did have a student who contacted me. Actually, it was not during my office hours. They caught up with me because I went past the math assistance area at 7 o'clock when I finished my shift in the advising area. I just stopped in there, and they came up and I said, hey, there's a student. Can you help this student? So I plugged in to help the student. But the student turns out is one of my students. I didn't realize that, and actually they didn't realize it either. But whenever we started talking, we realized that, oh, we were classmates that way. And anyway, this student asked a question, and so I'm just sharing the question with you. And I am going to answer a couple of questions that kind of I think are floating out there, so you don't have to ask those again. But you can ask whatever questions you want. This student was saying, yeah, Jim, I know, I understood you were going to record the video, but where is it? Well, here's the thing, and I'm going to tell you the same thing I told him, and he walked away happy. You see, when I record something, and I started the recording, Thomas, I think, didn't I?
Yes.
Good. Okay, so this is being recorded too. Here's what happens when I close off the recording. This is actually stored in Blackboard Collaborate Ultra. Now, I intend to upload these to YouTube and let you know, but they're in Blackboard Ultra as soon as they get rendered. Now, it takes a while to render because it has to be changed into MP4 and yada, yada, yada. So there's things that go. But anyway, I told this young student where it was, and he said, oh, I didn't know it was there. So you see, when you log on to Blackboard Ultra, before you go to the classroom, there are 3 little bars that are up in the upper left-hand corner of the screen. And if you pull those down, there will be a bunch of things, but one of them will say recordings. And so as soon as the recording is rendered, it's available there. So you can look at that. Now, I really did have good intentions of uploading that to YouTube, but I answered that student, and that student was very happy. So I thought, oh, well, I should tell my other students that's where they are, because maybe some of those students don't know where they are. So that was one where question that I got asked. Another question that students might ask is, okay, so what have we done? We did section 5.6 out of your book, and in a perfect world, you read that section, you reviewed your notes, and you, let's see, and you read those examples, and probably even did the homework problems. Now, those are just exercises to test if you are good with this. But anyway, that's sort of where we are, and that's where the videos are. And I am going to upload the PowerPoint slides, but I got distracted helping students and things like that, and so I haven't done it yet. But I will upload things that'll be called talking points, which is talking points 613, and I am going to upload those, but I haven't done it yet, because, and that's one of the reasons that when you're doing this, you shouldn't rely on say, oh gee, I don't have to pay attention, I'll just play with my cell phone. What happens is it is good for you to stay plugged in. But the videos are there. I plan to upload them to YouTube, and then I'll upload the other. So those are my answers to some where kind of questions. So I'm going to pause, and I'm going to count to 10 Mississippi to see if there's other questions that people are asking.
So this is Dale. I have a question.
Go ahead.
Yeah, yesterday you said that a third of our grade is based on low stakes assessments, and I was talking to a couple other people, and we're still just not sure what are they, what are they, and yeah, what should we expect for low stakes assessments and how we'll turn them in and stuff.
Well, okay, I will tell you a low stakes assessment that is kind of floating out there. Now, we're not to it yet. Well, actually, I guess what I will try to do during the break, and it was Dale, I think, what I will try to do during the break is I'll try to give you a low stakes assessment, okay? Now that means on the break, I'll have to go do some work, in addition to trying to get something to drink and going to the bathroom, but I'm capable of doing that. And so I'll try to come up with a low stakes assessment that I will share with you. But the clock will start with that whenever I do it. Okay? And so Dale, I hope I'm answering your question, because I'm saying, why don't I do an example of that today?
Not what I was expecting, but all right, thanks.
Yeah, and by the way, when people see this, they might say, "Thanks, Dale." But anyway, I know the thing I'm going to have to go find and do. I mean, I know what I do. It's just a matter of doing it. Okay, so Dale, I think your question will be answered well then. Okay. All right, I'm starting my count again.
I had a question. So like I was like just confused like in general about like how the grading breakdown is, because it said like there's like the low stakes assessments, the high stake assessments, then you said something like you round them to 100 points, or I don't know, like treat them as 100 points. Like I was just really confused.
Okay, well, please follow my example then. I don't know how many low stakes assessments we will have, because I'm just trying to teach you the best course I can. My number one thing is not your grade. I mean, I know that I have to give you grades and things like that, but my goal in life is not giving you a grade. My number one goal is teaching the best course I know how to teach. But Anyway, let's just pretend, and so please follow my example. You may want to write some of this stuff down. Suppose I gave you 8 low-stakes assessments, and I will just normalize them to be 100 points each. Now, or not, no, I'll just say when I grade it, I'll say, oh, okay, how did you do on this low-stakes assessment? So I give you 8. And I say, well, I'm grading each on a scale like that. I get 800 points. So we say, oh, I have 800 points on low stakes assessment. No, and I'm going to ask you to make up a number, and please don't say 800. Make up a number that is less than 800. I'm talking to the student that asked this question.
500.
How much?
500.
That's good. Okay, so what I will do is I will say, oh, well, this student, and it's not necessarily you, got 500 out of 800. So the way you normalize that is you take 500 divided by 800, and I can do that in my head. That is 0.625. Okay, so that means that student got 62.5% on the low stakes assessments. And I would round that to 63 just because it's easy to do, and I'll just round that up to 63. So that student would get a 63 that is normalized. So that is what normalization means. So if that student got 500 out of 800 on low stakes assessments, I would take the quotient of 500 divided by 800, and I'd say, oh, this student gets a 63 on that part of their grade. Now, I will tell you that that would be a little bit disappointing because the student can get help on the low stakes assessments, collaboration, talking to Jesse Hayes Carver, all that stuff is good. The work has to be your own because I want you to learn, but 65 isn't really a great grade. And in fact, generally speaking, I would expect your low stakes assessment should be perhaps your highest grade. Now, similarly, just continuing along with that vein, when I give you a test, it's not necessarily going to be 10 problems. It might be 12 problems. And so that would be, and if I just say, I'm going to arbitrarily say they're worth 10 points each, that would be 12 times 10 would be 120. I'm going to ask you to make up another number, please. Okay, so how many points did you get out of 120? And I'm not saying you, I know this is hypothetical. Just tell me a number.
80.
80, okay. Now you're being very kind to me because I can do that in my head too. That is 67%, right? Rounded up because it's 2/3. Okay, so the student would get on that test, and again, I'm normalizing things, but I'm saying, okay, so that would be a 67. Now I got to tell you, this student, this hypothetical student that we're doing, isn't doing as well as they want to, and they're going to, want to do a comeback on the final because neither one of those are actually especially good grades. But my intent here was not to talk a whole lot about grades, but what I wanted to do was answer your question about what do I mean by normalization. Are you good now?
Kind of like, I was more like asking like in relation to like our whole grade, like how much is like each type of assessment?
It is, okay, I'm repeating what I said before, but I'm happy to repeat it. 1/3 is low stakes assessment. So this student, this hypothetical student, 1/3 of their grade would be a 65.
Oh, okay.
1/3 of their grade would be a 67.
Okay.
And 1/3 of their grade, and I really don't want to do that calculation again, so we're not going to, or unless you need
No,
me
it's
to.
fine. It's fine.
But you see, and then 1/3 would be what they got on the final.
Okay, that makes sense.
And by the way, you might say, "Oh, gee, but Jim, when you're dividing by 1/3, things won't come out even." Well, I will round it up just a little bit, but that's what you get. So, and by the way, if I've ever say something and I'm sounding abrupt or rude, I'm not intending to be. In fact, once upon a time, I tried to go on a date, and when I went on the date, the person I was courting at the time said, "Hey, kill the teacher's voice." So I sometimes I'm talking like a teacher. I can't see you. I'm not trying to be mean or hurt anybody. Your questions are always welcome. And I hope I answered your question.
Yeah, you did. Thank you.
Excellent. Okay, that's great. Okay, I'm starting to count again. Okay, I hit 10, Mississippi. Again, your questions are always welcome, but we're going to now move on. Just so you know, let's see, what do I have? I have a Fitbit today, so I am looking at the Fitbit, but we're going to be doing the protocol of 75 and 50, okay, meaning more or less at 9:15, we'll take a break for 10 minutes, and then we come back and we finish the class. And so the first segment of the class is longer than the second segment of the class. We already did the end quiz, so we're going to start with new material. So here we go. This is the end quiz. We don't need to talk about that. Okay, now today we're moving into a different topic, and we're going to be talking about volume. And before we're finished with volume, Thomas, you can hear me, yes?
Yep, we're all good.
All right, excellent. Okay. All right, this is kind of the program. We're going to be talking about volume, and volume, of course, areas would be like square meters and volumes would be like cubic meters. And we're going to talk about different ways to do this. And today we're going to talk about a technique that in my notes here, I call them the disk method. In some textbooks, and some of you might be, coming from other schools where they have different textbooks, and that's all fine. Sometimes this is called the ring method. And sometimes this is called the, this also has a version that's sometimes called the washer method, and there's also the ring method. But I mean, don't worry about what it's called. But what we're going to do is we're going to be talking about finding the volume of a solid of revolution using what's called the disk method. Now, a variation on this is we're going to talk about finding the volume of a solid of revolution using the washer method. And then the third thing that I'm planning on covering with you today is finding the volume of a solid with known cross-section formulas. Okay, and this is actually going to, even though it is volumes, it's going to build heavily on what we did before, and we will be talking about integrals here as well. So that's what this, lecture is about. Okay, so we're going to talk here. And if we were in a classroom, I would call on people like I might call on Dale. And Dale, I'm not calling on you now, but that's the name I remember. So I might call on Dale and I say, hey, Dale, please read this for me. Unfortunately, we can't do that. And so you're just listening to me, and that's what we've got. So anyway, here we go. You've already learned that area is only one of many applications of the definite integral. But another important application is finding the volume of a three-dimensional solid. And so in this section, we will be studying a particular type of three-dimensional solid, one whose cross-sections are similar. That is, they're the same geometry. Solids of revolution are commonly used in engineering manufacturing. And some examples are axles, funnels, pills, bottles, pistons, and so on and so forth. And so there's pictures here of these things. Now, I actually have had students in the past, and who knows, maybe some of you, who are involved in actually manufacturing processes making these. And these are based on calculus. And if we're figuring out the volume, for example, let's suppose I'm wiggling my finger at this, I don't know, engine part or something here. If somebody's making these engine parts, you want to know, well, how much does it cost us to make that engine part? So you'd say, well, we're making them out of, I'm making up something, but we're making out of aluminum. So if you're making this out of aluminum, the density is equal to the mass over volume. So once you know the volume, you know what the mass this is. You can figure out how much this costs and, things like that. So this is a very useful thing. So we're going to be looking at figures that look like this. So this is a very applied kind of thing. And again, your questions are always welcome. Every so often I will pause and say, hey, are there questions? But, I won't do that on every slide. So shout out your questions when you have them. Okay. Okay, now a solid of revolution is what we're talking about here. So this is the definition. And I'm not going to ask you the definition, but you do have to understand what the definition is about. So here's, again, I'm reading to you. When a region in a plane is revolved around a line. So you got something in the plane, but you're revolving it about a line. The resulting solid, and you say, oh, is that a solid? Well, you'll see that that's a solid. So you got a line that you're revolving around. The resulting solid is a solid of a revolution. And the line you're going around is called the axis of revolution. Okay, and we'll do examples and so on and so forth. The simplest such solid is a right circular cylinder or disk, and this is called the disk method. Okay, so a disk is a little bit like a can of chili, if you bought a can of chili, because the chili has a height, it has a circular, I mean, it depends on the can of chili, I know, but it could have a circular top, a circular bottom, and could have you know, it has a height. So that would be an example of a right circular cylinder. And the reason it's called a right circular cylinder is because the line joining the center of the top and the center of the bottom is perpendicular to the base. Now, this will make a lot more sense when we look at examples, but this is formed by revolving a rectangle around an axis adjacent to one side of the rectangle. And it says as shown in a figure. Now, I'm going to go to the figure just so you can see it. We'll come back to this slide. Okay, so here's the thing. Okay, and now what we're saying is, oh, the axis of revolution is this line here, the horizontal line that I'm kind of wiggling my my cursor about. Okay, and here is the rectangle that I'm revolving this around. So what happens is, and by the way, this is some notation, tradecraft. So what we're doing is we will say, and we will often draw a little arrow like this to say, oh, I'm revolving this rectangle here around this axis. So you see what you're doing is you're spinning, and I can do this better in person, but basically what you're doing is you're grabbing a hold of this, and you're grabbing a hold of this, and you're holding this firm with your left hand. Let's see, I'm going to say with your left hand. And with your right hand, you're treating this rectangle like a propeller blade, and you're like whipping it around like that. And so it's going around this way. But you're saying, what volume does this do? Well, if you think about the volume, and sometimes I tell my students, think about if your eye is out here, you know, what do you see? Well, when this goes around, what happens is you sweep out, and here it's called a disk. So this is the disk method. But when you're going around, you see that this is W by R, but this is the axis of revolution. And so if you do that revolution, what happens is this remains W up here, but it goes around like this. So the radius that you see, the distance from the axis to the top of that, is R as it goes around. So this is a three-dimensional object. So this would be, this circle here would be the top of the can of chili, the bottom of the can of chili is over here, and the height of the can of chili in this little story is the W. Okay, I'm going to pause, but I'm just going to count to 5.
Super quick question. Is radius usually capital R? Just my vague memory is lowercase r, but it's been a long time for me. So is that standard, capital R for radius?
The answer is going to be yes and no. Okay, and unfortunately, that's the true answer. And my general thing, and by the way, I'm not trying to be a wise ass when I say this. It can be anything you want. Okay. Now here we are using capital R, but later in the same lecture, we're going to talk about the washer method, where there really are 2 radii going on. And so this is we typically would use a capital R for the larger radii, and we'd use a lowercase r for the lower. And again, I'm not trying to be rude with my answer of it can be anything we want. But yeah, in these formulas, you want to think about that as being capital R. You okay?
Yes, yes, thank you.
Good. Okay, excellent. Okay, so I'm counting to 5 again.
Could you go back to the last slide for a second?
Oh, I have to go back to that one anyway, but thank you. Okay. Hey, I tell you what, I mean, and I'm interested in your question, and of course I did go back to the slide, but now let's talk about it. Now I'm going back to that slide, but I'm coming back to this one, so I'm doing what you want. Okay, so you say, well, what the hell is the volume of this? Well, the volume of this, now, and this is a right circular cylinder. So you see what happens is it's going to be the area of the top of the can of chili times the depth of the can of chili. Now, and when we're doing this, if this were the x-axis, then what we have is we got a circle going on here, and the area of a circle is pi capital R squared. But then it has to be a volume, so you say, well, what the heck is this W? This W is going to be delta X, okay? Or it could be delta Y. It's going to be a delta something. So now I am going back as the student requested, and now I'm talking about this. Okay, so the simplest such solid is the right circular cylinder. I showed you a picture of that, or cylinder or disc, and we talked about that. I showed you the picture. But the volume of such a disc, now this is the part that I didn't say yet, and we should say this is really quite important. So the volume of the disc is the area of the disc. By the way, the area, when they're talking about the area of the disc, they're really saying the it's the area of the circle, okay, times the height of the disc or the width of the disc. So the area of the circle on the outside is pi capital R squared, and it's W, where capital R is the radius of the disc and W is the width. Now, very soon, we're not going to be talking about W's and this. Very soon, we're going to say, oh, we're going to call that delta X. Now, I am going to pause in case that student who was asking me to go to the slide, if that helped and maybe answered her question.
Oh yeah, I just needed to write down the formula.
Yeah. Okay, so are you good now?
Yes, thank you.
Okay, excellent. All right, so then we, and we talked about this. I don't think I'm going to count to 5 again. Your questions are always welcome. Just leap in and do your question. Okay, but now here's what we're going to do. So to see how to use the volume of the disk to find the volume of a general solid of revolution, consider a solid revolution formed by revolving the plane figure in 714. So I'm down here looking at this picture. So you see this black curve here is some kind of function. It's like f of x, if you want to say that way. So this is y equals f of x. But now what we're going to do is we're going to revolve this. And in this example of these pictures, we're resolving this around the horizontal axis, which we could call it the x-axis. So you see, if we're building something that looks like this, I'm just talking about the middle thing, what we're going to have is we'll say, well, we could approximate that by these disks. So I would have delta x there. That would be that little rectangle that I drew. That is called the representative rectangle. And then we have this plane area. So it's going around there. That's what I'm doing. But now I'm going to, and this is that accumulation function. So you see now what I'm going to do is I'm going to say, well, yeah, the rectangle is this size here. It's going to be a bigger rectangle over here because it's taller. It's going to be a smaller rectangle over here. But I'm going to take the limit as delta x goes to 0. So let's go up here. So I talked about the picture. And so we're revolving the plane figure in that picture. That's down here. It's not on the next page. About the indicated axis. So determine the volume of the solid. We're going to say, well, every time the volume of one of these little disks is going to be delta V is equal to pi capital R squared times delta X. So this is an important formula for you to write down. And so this is the representative disk. Now it's not going to surprise anybody, I think, that we're going to take the limit as delta x goes to 0, and we're going to integrate all of these things. And so this delta x is going to become a dx, and that's how we're going to get the volume. Okay, so, but here's some more discussion that we had. Okay, so we go here. Now, all of this stuff really just says, oh, if I add up all these rectangles and take the limit as n goes to infinity, this volume of the solid, this is the limit as, well, it's the same thing as n going to infinity. But you see, here's the formula. It is pi r squared, but r is different in each of those rectangles. So this is actually r of x sub I. So it's r of x squared, and then this is delta x. So in the limit, this volume of the solid becomes pi. And by the way, an important thing to remember is pi r squared. But we have pi. We integrate from a to b. And this is the function, capital R of x whole squared dx. And again, you can jerk the pi outside. You might say, well, I want to leave it inside. I don't care, but I will tell you that 10 times out of 10, as a practicing mathematician, I will jerk that pi through there. Okay, so that's our formula. So we're getting close to doing something useful. Okay, so now we're getting a formula for that. So this is what the disk method looks like. Okay, so I take a known, and by the way, you might say, oh, this looks a little familiar. Well, we talked a little bit about this last time. So we're taking a known pre-calculus formula that the volume of the disk is pi r squared w. But if I slice things into pieces, and notice I did do in this one I did vertical slices. So I say delta v, the representative element there, is going to be pi, and this is r, and it depends on where I am, what the rectangle looks like. But this is r of x sub I whole squared delta x. But when I take the limit, I get that the volume is equal to pi, the integral from a to b. You have to figure out what a and b are often. But then this is r of x whole squared dx. So this is the formula that you want. Now, a similar formula can be derived when the axis of revolution is vertical. And I'm thinking that the next slide has both of those on it. Okay, so here it is. So to find the volume of a solid of revolution with the disk method, one of the formulas below will be used. So either we're going to do pi, the integral from a to b, capital R of x whole squared dx, or if we draw the slice the other way, it is that the volume is equal to pi, the integral from c to d, r of y whole squared dy. Now, you see, drawing these slices is really important, folks, because you see, if I draw this slice, right away I know it is dx that I'm doing when I draw a vertical slice. So that means this has to be an r of x that I'm squaring, and that is dx. So they got these little arrows here. That's actually very nice. And then, now notice, though, that here what we're doing is we're going around the x-axis. So we drew the slice x, we're going around the x-axis, and that's our formula. If we're going around the y-axis, which sometimes we are, the slices should be drawn this way. And now I'm going to say something that is really worth writing down. Oh, and you might say, well, Jim, why don't you write it down? Maybe I will try to write it down. Let me see if this works. Okay. In the disk or washer method, comma, the slice is drawn perpendicular. I have to figure out if I can spell that. Is drawn perpendicular to the axis of revolution. Now, didn't do that right. Revolution, I think that way. Okay. And since I did this, I guess damn it, I will try to make this red. And you might say, well, why do I care about that? Well, the reason you care about that is very soon, not in today's lecture, but probably tomorrow's lecture, we will not be talking about the disk or washer method. We're going to be talking about a thing called the method of cylindrical shells, which is different than this. And so that's why that's an important thing. And I've taught this course many times, and I will tell you that that's a useful, that little red thing is a useful thing for students. I'm going to pause and we're about ready to do an example of this real soon. In fact, you know what I think I'm going to do? I think what I'm going to do is I'm going to wait till the example before I poll for questions. Your questions are always welcome, but I'm not polling for questions right now. I'm just going to keep going. Okay, and maybe this says this. This probably says exactly what I said. Ah, yes. Note that you can determine the variable of integration by placing a representative rectangle. I call that drawing a slice in the plane region perpendicular to the axis of revolution. So in the disk method, you're always drawing your slice perpendicular to the axis of revolution. That is really useful because that tells you, am I going dx or dy? You might say, well, that should be obvious to anyone. And I will tell you, students don't find that obvious. So if you're doing, anyway, it's perpendicular to the axis of revolution. And if you're doing delta x, it's going to be dx. And if you're doing delta y, it's dy. Okay, so let's just do an example now. And so we're going to wade through this example. And at the end of this example, I certainly am going to pause to see if people have questions. Okay, I'm going to read this to you because that's the only way we can do it right now. Okay, so we're to find the volume of the solid formed by revolving the region bounded by the graph of, it doesn't say y equals f of x, but y is always f of x. So this is y equals f of x equal the square root of sine x. And then it says in the x-axis. Now what this means is, oh, I'm revolving this around the x-axis. And I'm revolving this from 0 less or equal to x, less than or equal to pi. And now it says about the x-axis. So I guess I didn't say, okay. Anyway, and it does say as shown in figure 716. Now I want to tell you that I would not ask the question exactly this way because, and I guess I'll, let me go and do a thing here. I'm editing this on the fly, but this maybe is good. Okay, so I'm just Xing that out because you see, I would, and I will save this just so I have this. Okay, you see, that would be the way I would ask the question. And and you might say, oh, you mean I have to graph it? And the answer is yes, you do have to graph it. So, you know, sketching this graph is an important part of getting the problem done. And in fact, that's probably your first step in getting this problem done. Okay, and by the way, they did not tell you, it didn't say, oh, use the disk method, although when we look at the picture, you're going to say, oh, it's obvious that I can use the disk method. And I guess it's a little bit obvious because that's the only thing we've talked about so far. But anyway, so now we're going to continue with the problem example 1. And again, I am going to pause for a count of 10 Mississippi at the end of this, this example. Okay, so your first step is you have to sketch this. So one thing you probably want to do is draw X and Y axis in your sketch, and then you want to probably make a little thing like this to say, oh, I'm going around the X axis, because you see that makes a difference what you get. So we're going around the X axis, and then we have to say, well, what does this graph look like? Well, this is y equals f of x, which is the square root of sine. Now we're going from 0 to pi, and the sine of x is positive from 0 to pi. So all these are real values, and it doesn't look like the sine curve exactly, but you see the sine of pi over 2 is 1. So if you sketch the square root of the sine curve, it's compositions, and we get this, and the sine of pi is 0. And so this is what the sketch of that function looks like. Okay, so what we're doing is we're taking this, this area, but we're whipping it around the excuse me, x axis, and that gives us a three-dimensional figure. And so if you're saying, well, what's going on here? This is what the three-dimensional figure is going to look like. So we're finding the volume of this. It almost looks like a football, doesn't it? And some of the students who know about football say, oh, football really doesn't have this equation. I know, but it kind of looks like a football. Anyway, it is what it is. So this is the solid revolution that we're going to have. But now, what are we going to do? Well, so first step would be graphing it, and you're graphing it without a graphing calculator, so you have to be able to graph it. But then, next thing you're going to do is you want to draw a slice. So here is the slice that I draw. Now notice that I am drawing this slice perpendicular to the x-axis. That means this is perpendicular to the axis of revolution, which means, oh, I can use the disk method. So what I have then is, here's my, and sometimes I tell students, well, look out here. So when this thing goes around, the radius is going from y equals 0 up to y equal the square root of sine x. Now you see that varies as you go along. So here you have this one, but here it goes up higher, and down here it goes lower, and down here it's lower. But you're doing you're just adding all these things up, and we sort of talked about the accumulation process. So this really is just going to be an integral. Okay, but I want to make sure that you understand the picture. That's what I'm trying to do here. Okay, so now it's really time for us to just evoke the Euler formula, because r of x is going to be the square root of sine x, pi is going to be pi, and delta x is going to become dx, and I'm going to go from 0 to pi. Okay, so here we go. So the volume, now I'm really cutting to the chase here, but this is going to be, in fact, I'm going to skip this a to b because they told us what a and b were in this problem. So it's going to be the volume is equal to pi. It is an integral from 0 to pi. And then the r of x in this problem is the square root of sine of x. But then I have to square it because the formula is pi r squared. So this is squaring the square root, which is easy to do. And so we'll just keep, and now you have to calculate the integral. And by the way, to get credit on the problem, you do have to finish the problem. And that is, you are computing an integral. But here's the thing we need to do. Now, when you square the square root of sine x, you get sine x. And so this is what we're going to do. So this is the integral from 0 to pi, but it's times pi. So there's going to be a pi in your answer of sine x dx. So now we have to integrate this. So the antiderivative of the sine of x is the negative cosine of x. The fundamental theorem of calculus, I'm going to evaluate it at these things. Now, when I put pi in, the cosine of pi is -1. So that is a minus 1. And then there is a minus that from the fundamental theorem of calculus. And when I put it at 0, I get another minus, but that's going to be minus 1 minus a minus 1. So it is 1 plus 1 is going to be 2. So the answer is 2 pi. Now, you're not using calculators here. And so the correct answer to this problem is 2 pi. Now, I'm finally going to pause, and I realize that, maybe I have to go to other slides and things like that. But we've now done an example, which is good. I think this was a good example of using the disk method. So I'm going to pause for a count of 10 Mississippi. And if you got questions, this is a good place to, try to leap in.
I have a question on
Yes.
I'm quite confused as to why the volume is pi r squared, just like the integral.
No, well, okay.
Could you sort of re-explain that? Yeah.
Yes, I will. But I'm going all the way back to here to answer your question. And I'm disagreeing with you, and I'm not being rude, but I'm just saying, no, what you said something that is at the heart of your misunderstanding. The volume is not pi r squared. The area of the top base and the bottom base of our cylinder is pi r squared. That is a volume, that is an area, but the volume is pi r squared times delta x, or dx. So you see, if I'm talking meters, r squared would be square meters, but this is another meter, so that is cubic meters. Now, I hope I'm not saying that in a way that sounds harsh, but that's the answer to your question. So it is a volume because it's the area here that's pi r squared, but it's not volume until I do the dx or until I do the delta x. But we did. Did that help?
Yeah, thank you.
Okay, great. And again, I appreciate your question. So I know I probably sound rude all the time, but I am not trying to be rude. Okay, and I always start my question or my count again when people ask a question.
So I have a question. This is Dale.
Yeah, go ahead,
So I'm not quite following why pi is outside the integral, but the r is you're taking the integral of the radius squared.
It doesn't matter. But one of the things you learned, and again, if I were in a classroom, I could easily draw this, but I'm just going to ask you to understand. If you have the integral of a constant c times f of x dx, that is equal to c on the outside of the integral, f of x dx. So you see what we're doing is we're pulling that constant out of the integral, which is one of the things we learned you could do with limits, and the definite integral is a limit. So the pi is on the outside because you pull it out. You could have left it inside and still done it, but just a good tradecraft thing is, and I got to tell you, as a practicing mathematician, I pull that constant out 10 times out of 10. Did that answer your question, Dale?
Yes, thank you.
Okay, excellent. The count starts again. Okay, we hit 10 Mississippi, so we keep on going. I do know what time it is, and we probably have time to do example 2, which is really great. Okay, all right. Now, this problem is a little bit different, and actually, I don't like the way that's showing up on my screen, so I'm adjusting it a little bit. There we go. Okay, so, and I will save that important change. And I'm just going to read this. Now, this is a harder problem. Or, now, I shouldn't say that. This is a different problem. And in fact, this is going to talk about the washer method. And so find the volume of the solid formed by revolving the region bounded by the graphs of. Now, you see, so one of the graphs is y equals f of x equal 2 minus x squared. And another one is g of x. And we're rotating this about the line y equal 1. Whoa, that's a different axis rotation. It says as shown in the figure. And I guess I'm going to tell you that I am not going to be doing that. You will sketch these things yourself because that's what you have to do. So I'm going to show you this as we go through it now. But no, you have to sketch that. So I'll save that change as well. Okay, so let's see, what am I doing? Here we go. Okay, so that's what the problem is that we're tackling. Okay, well, the first thing is going to be you need to draw all this stuff. So let's plow in. Now, g of x equal 1. Well, g of x equal 1 is y equal g of x equal 1. So that is y equals 1. So you see here is 0, 0. This is the xy plane. But here is 0, 0. So the line y equal 1 is up here with this guy. So that's what you're going around. So you draw the line y equal 1, and then you put this little thing saying, oh, that is the axis of revolution. And then your top curve is f of x, and you don't know this till you graph it, but the top curve is y equals f of x equal 2 minus x squared, and your bottom curve is g of x equal 1. And you see what you're doing is you're taking this blue stuff and you're spinning it around this y equal 1 axis of revolution. And so the solid that you get looks like this. And if the other one was a Tom Brady football, this is a real football. That is inside joke. Don't worry about understanding that. That doesn't matter. Actually, I'm a big Tom Brady fan. I like it when old guys do well because I'm an old guy. Anyway, so we got this going on. So we're spinning this around, we're getting this. So my representative rectangle then is here. And notice that we're drawing our slice perpendicular to the axis of revolution, because that's what we do when we're doing the disc or washer method. Okay, so we draw that perpendicular there. And that's kind of the picture. This is going to be delta, it's going to be dx eventually, but right now it's delta x, so we drew that slice. But you see, that helps us really, really, really a lot. So I'm going to then move on, but you see the first step is drawing the picture, and I expect you to draw the picture. I don't give you the picture. I mean, I am in these examples just so we can move along, but okay, so there we go. Let's go to the next. Now we're going to use the formula. Okay. Now, one thing we have to do is we have to figure out, well, what are these points? What is this point and this point? You might say, well, it's obvious from the graph, it's -1 and 1. No, you sketch the graph. You don't know that yet. Or maybe you can do it in your head. I don't know. But you have to know what those are. So we say, well, where do these two curves intersect? And I had an f of x and I had a g of x, okay? And in fact, what's the radius? And so the radius that we get is going to be f of x minus g of x. Now I'm going back to the previous slide. See, the radius goes from, this was g of x down here, this was f of x. So the height of this, the r of x, capital R of x, is going to be the difference between the two. So it's the guy on top minus the guy on bottom. And so it is 2x minus x squared minus 1. Actually, it's g of x. So we will go back to the next slide then. So you see, this is going to be 2 minus x squared whole squared minus 1. But if we take 2 minus 1, we get 1 minus x squared. And that tells us where the two things intersect, because when is this equal to 0? When do they intersect? Setting the two things equal to 0, you get this, so it's -1 and +1. So that means that the volume, okay, of this is equal to pi. And again, I told, I think it was Dale, but I told somebody I will pull that constant out 10 times out of 10. I do that. Okay, but anyway, it is pi, the integral from a to b of r of x dx. But we found out that r of x from this problem was 1 minus x squared. But now, please understand that r of x is 1 minus x squared. But what I have to do now is I have to square the whole of 1 minus r, or 1 minus x squared. Well, I don't know how you do that. I know how I do that, but you can... I don't know, you can do FOIL or whatever, but you have to multiply this out. So you see, there's quite a bit of algebra that you maybe have to do. It really depends on how good you are at algebra. I could do this pretty quickly. But when you expand that, because you can't integrate it this way, you might say, well, can I use U substitution? No, you can't use U substitution, because you see, if you were letting U be this guy, you would have a 2x. So your only thing is you have to square it, multiply it out. So you see, this finishing this problem would take you a bit of time, because you have to do all of those things. But when you square 1 minus x squared whole squared, you get 1 minus 2x squared plus x to the 4th. And I have to integrate this term by term. Okay, so when I integrate 1, I just get x. When I integrate this, I would pull the 2 out, and I would say I'd add 1 to the exponent, divide by the new exponent. This is x cubed over 3 times 2. And here I add 1 to the exponent, divide by the new exponent, and I get x to the 5th over 5. And then I have to use I'm going to hide this so you can see. Now, there is a pi in your answer, and you might say, well, what if I drop the pi? Well, you don't get full credit, because that is not good. Now, if you had everything else right and you said, oh, it's 16 over 50, I'd say, well, bad news for you. You lost your pi. So, you know, this is the answer that you want to have. And I don't want to get into grading rubrics and stuff, things like that. But the answer is 16 over 15 times pi. Now, I realize we're almost at a break. And I'm really trying to figure out if I want to poll for questions before the break, and I think I don't want to, actually. Now, please understand, when we return from the break, I haven't given you the break yet, but it's almost here, and I'm looking at my Fitbit now, so it is what it is. first thing I'll do when we come back is I'll say, hey, do you guys have questions about this problem? Okay, so we'll do that, but we'll do this after the break. Okay, so it is 9:15. Is this class well run or what? So we will reconvene at 9:25. Okay, we're on break now. 9:25, we return. Hey, Thomas, can you hear me?
Yep.
All right, good. We're coming back into play here. And Thomas, stay with me for one more moment because I'm needing to share something. Here we go. So I'm sharing my application screen again with you guys. And okay, so what you should be seeing, Thomas, is a PowerPoint slide. Is that what you're seeing?
Yeah.
Okay, good. Thank you. And again, Thomas, I know it sounds tedious and everything else, but you're really helping me a lot because I have no idea what's happening out there. I have no vision into your space. I am going to do what I said, but I also promised that there would be an LSA1 because Dale asked for this. And by the way, if we were in a classroom, I would say, hey, on the count of 3, everybody please say thank you, Dale. But anyway, here's an LSA1 just to, get us started along this. So LSA1, it is in these PowerPoint slides. So consider, and actually I should change this a little bit. I don't know, I need to make up something. So today is Tuesday. I'm going to say this is due. Now, by the way, these are due dates, and when I'm talking about due dates, then students say, "Oh, I need an extension," and things like that. Well, I'm doing a due date just because we should have a due date, but and in fact, I think I'm going to say that this is due at midnight on a certain date. Now, and you say, "Oh my God, I didn't turn it into 1 o'clock." Don't worry about that. Just because my number one thing is teaching you a good course. But anyway, and there will be protocols for turning this in. Jesse Hayes Carver will invent something where you upload it or something. I haven't talked to Jesse about this, so I hope he is okay doing this. I know how to do it too, but I'm juggling a few things. Okay, so anyway, I'm going to say this is due, and I need to look at my calendar here. Damn it, that's not the calendar. Hold on. Okay, so Sunday is the 19th. Oh, wait. Oh. Before midnight. And you might say, well, what's Jesse Hayes Carver going to put there? He's probably going to put 11:59, but before midnight on June 19th. Is that Juneteenth? I don't know. Anyway, okay. All right, so that's the LSA. There is a due date, and their uploading protocols will be described later. I don't want to deal with that right now, but Jesse will make sure you can upload PDFs. And again, take-home protocols apply. So if you say, wait, I struggle with this. Well, that's okay. Can be some working together. What I don't want you to do is go online and ask Chegg about this. First of all, Chegg pays people whether the answers are correct or not. And this is about learning. It's not about copying from Chegg. But anyway, and I'm not trying to police that anyway. I don't care. But anyway, here it's so the problem is, consider the y equals f of x is equal to the absolute value of 2/3 x cubed minus x squared minus 11 over 3x plus 2. Now, this probably wouldn't be a great exam question, because when you start doing it, you'll kind of say, oh, wait, there's some complications here, and there's all kinds of fractions and everything else. So this maybe isn't an excellent exam question, but it's a fine LSA question. And what I'm asking you to do is graph this function. And then I don't know if it's parts A and B or what, but anyway, it is graph this function and then find the area of the region between this curve and the line x equals 0 and the line x equal 4. Okay, so I'm going to pause here for a moment. And Dale, since you brought this up, does this help?
Yes. So low stakes assessment questions will be given in class, due outside of class, and I assume
I don't know when they'll be. Yeah. Generally speaking, yeah. And the only reason I did this today was because I was trying to answer your question. I think this is a better answer for your question. Now, there might be someday when I say, oh, I posted something and I'll let you know. I mean, I don't know. I do whatever I think is most useful for the learning. So anyway, Dale, I hope this helps. Okay.
Yeah. So will this be posted on Blackboard as well? So like let's say I miss class, I'm following along on Blackboard.
Well, what I would expect a serious student to do would be to come to class to see this and to know it's there, maybe even have already written it down so it's there. Now, Jesse Hayes Carver may choose to separately post this and stuff like that. And it really depends on how much, how much he chooses to do. But you see, my number one thing is teaching you a good course. It's not, stacking things up. So people say, oh, there's LSA1, things like that. Now, maybe Jesse Hayes Carver will he has done this in other courses. He's created an LSA folder for those who need such structure, or for people who aren't here, and things like that. There's a bunch of students that say, I'm working full time, so I'm just going to watch the videos. Well, I hope they know what they're doing, because that's not actually an easy way to go. Anyway, so Dale, this is LSA1. I don't know what will happen with LSA2. And again, I'm not trying to be rude. I'm just being honest. Okay?
So the answer is maybe.
Did you say maybe?
Yeah.
Yeah.
So to the
That's
question
a
of
good
will
answer.
this be on Blackboard, the answer is there's maybe.
Well, I think eventually this will be on Blackboard, but it's probably going to be in the slides that I post when I get around to posting them. That will be called Talking Points 613.
Okay, thank you.
And I know maybe some students will say, oh no, we need a separate tab that just has LSAs, and who knows, maybe Jesse Hayes Carver will do that, or maybe I will find the time to do that. I don't know. So, but anyway, this is the answer to your question. This is what an LSA is, and now we have one that's due. So there is something in play here. Okay. And please understand, Dale, I was not trying to be rude in anything I said. So, okay. What were we doing here? Oh, we did this problem. And I'm hiding this thing telling me that I'm sharing, but this is the problem that we just did. And I promised you that first thing I would do after break, and we're back from break. And just so those of you who say, well, what's happening now? Well, as usual, we'll have 50 minutes. So we're going to let's see, what do I want to call it? 10:15-ish is when I'll dismiss you. Okay, so anyway, I talked you through all of this, so I'm pausing for a count of 10 Mississippi to see if people have some questions. And again, I'm going to ask you just to shout out, because So anyway, I'm starting my count now.
So, Professor, if you can go back a slide.
I can. Oops.
Or, sorry, the one where it was talking.
Is this the slide you want?
Just one more back, sorry. It's the one where it says y equals. Yeah, right here. So then about the line y equals 1, what does that have to do, like when we're drawing it, where do we implement?
Oh, okay. So now, and here's where that answer is. You see, you're revolving it around y equal 1. So this is the xy plane. This is 0, 0 that I'm pointing at right now. So this line that I'm kind of, doing with my cursor, that is the line y equal 1, g of x equal 1. And that's what we're revolving around. Now you see that changes everything because you see we're revolving this around y equal 1. If you look at the picture down here at the bottom, you see, oh no, we're not going around the x-axis, we're going around y equal 1. So, and I tried to do a joke that probably went flat, just like Tom Brady's footballs. But anyway, this is an overinflated football, I suppose. But you see it's going around and it is kissing the x-axis down here. Now, where does that enter into play? Well, it enters into play whenever you're talking about what is capital R of x, because capital R of x then is the height of this rectangle. And so that is this top function minus the bottom function. And so that's how we got the 1 minus x squared here. Did I answer your question?
Yeah, thank you.
Okay, good. Okay, I'm starting my count again. Okay, I hit 10 Mississippi. Again, your questions are always welcome, but I do that just to keep this moving. Okay, we're going to do another example. Now, and I know I'm just reading to you. It says the disk method, the idea that we had, can be extended to cover solids with holes. And by the way, that's why this is sometimes called the washer, because there's a piece of hardware that you can get that has a hole in it, and it's called a washer. Okay, so we're extending this to cover solids of revolution that have holes, and we replace the representative disk with a representative washer. And I don't remember who I was talking to who was asking about that capital R, but we're going to see a capital R, and we're going to have a lowercase r. Now the washer is formed by revolving a rectangle about an axis, but we're talking about a washer, so this is it has a hole in it. And if lowercase r and uppercase r are the inner, so the inner is the lowercase, that's the smaller number, and the capital R is the outer radii of the washer respectively, and W is the width, then you get the volume of the washer is pi capital R squared minus lowercase r squared W. Now let's look at the picture to really understand what's going on. Okay, so this is a situation where your representative rectangle is shown up here. I'm wiggling my cursor there. So that's the representative rectangle, and it's being revolved around this as the axis of rotation or revolution. But this rectangle is not sitting on the axis of revolution. It's floating in the air above this, which is capital, it is floating above the axis of revolution, lowercase r above. So now what you really want to think about is, okay, I'm going around this thing with this, but there's a hole there. And some of my students like to call these donuts instead of washers. I don't care. That's okay. But you can think about your eyes over here. So when this goes around, you see there's going to be a hole in the middle. And the hole in the middle is going to have a radius of lowercase r. And if I go all the way from the axis all the way up to here, it's going to be r. So you see, and I am getting a disk. This is a three-dimensional thing. A student asked about this before, because you see there's the area of the top thing is meters squared, but when I have the W, that gives, let's see, how do I want to say this? The dx, or the thing that's playing the role of W, makes it meters cubed. Okay, and if you look at this picture, you say, well, how would I ever find out what this area is? Well, you would take the area of the whole disk with that hole there, and then you would subtract off what was missing. Okay, so here we go. To see how this concept can be used to find the volume of a solid revolution, we're going to consider, I'm just writing it down here, but that's what we have. So you see it's going to be the difference between the disk method, so that would be the pi capital R squared of x, but then we're subtracting off the disk that we cut out, and that is going to be pi times lowercase r of x squared. Now, please remember this formula. I mean, and a student asks, I don't know if it's in your class or in your sister class, they say, oh, we'll have a formula sheet, right? No, you won't, because that's the way we do it in the math department. And I'm part of the math department, and I play on that team. Anyway, but this, you see, you could have the common pi out here, because there's a pi on both of these things. So you could have the pi pulled out here both times. But you're going to compute this, but you see it as the difference. This is r of x whole squared minus lowercase r of x whole squared dx. And this is called the washer method. Now let's look at a real example of that. And actually, I don't know if this, I mean, yes, this is a real example, but it's still a little bit of a theoretical thing. So suppose I said, oh, okay, so we're going to take this blue hunk of area here, but we're going to revolve it around this axis. Okay, so there's that blue area that you're taking around that axis. Well, you see, if you start thinking about that, what you have is you have the disk method, so that is giving you the capital R of x that goes to the function that is on top, and you have the lowercase r of x that's going to the function on bottom. So when you rotate that around and you think, well, what do I get with this? You get a solid of revolution, but it has a hole in it. And okay, so here's a note. I think I said this, but let's say it again. Note that the integral involving the inner radius represents the volume of the hole and is subtracted from the integral involving the outer radius. And I think I said that. That's just what the formula here says. Okay, now I think I am certainly going to allow you to ask questions, and your questions are always welcome, but I'm not polling for a question. I think it'd be better to actually do an example of this first. Okay, so let's go and look at an example. And again, I'm going to change this just because I don't want students to say, oh, he's always going to draw pictures for us. No, I'm not doing that. So this really isn't there. I'm drawing a picture for you now, but this is the problem that we're going to have. I should save that, I suppose. Okay, and Thomas, you guys still out there?
Yeah, we can still hear you.
Excellent. Okay, so this is called example 3. I'm going to read it to you. And this is the way you would find this manifesting itself on a test question or something, I suppose, a high stakes kind of thing. So find the volume of the solid formed by revolving the region bounded by the graphs of y equal the square root of x and y equal x squared about the x-axis. Okay, so that's what you've got. And if we were in a classroom and things were different, and this was a regular term where we weren't doing double time, I'd probably say, yeah, everybody give this a go and see how you do, and then we'll do this. And who knows, there might be a question like this as an unquiz tomorrow at the beginning of class. But anyway, so here we go with, well, okay, so that's the statement of the problem. Hope people understand that. Okay, first step is you need to graph these things. And you need to think about what are we revolving about. So we're going to graph them first. And again, you have to graph them, and you're graphing them without a calculator. Okay, so here's what the graph looks like. And by the way, I don't think I did this problem. I did a problem like this with you, but I actually did it with your sister class. It's a little bit funny because your sister class meets beginning at 11, and so we will adjourn, and again, don't worry about this. It's not a significant thing, but I'm maybe a little bit more agile when I teach the second class because I'm really teaching fundamentally the same material. But I have additional examples that I might do because I'm aware of that. I say, gee, I might be faster or quicker or anticipate questions better. And so sometimes they might have an extra example or something. And if we go fast enough here, you'll get those extra examples. I'm prepared for that. Anyway, here's the picture. So here is the graph of y equal the square root of x, and you're supposed to know what that looks like. So there it is. And here's the graph of y equal x squared. Now, neither one of those is very complicated. And what you can do is then you can figure out, well, what are these points of intersection? And so you can say, well, when is the square root of x equal x squared? And you can work through that, and you can figure out when that is. And we'll talk a little bit about that. So I get this picture. But then you're going around the x-axis, which means you draw a little gadget like this down here because that's what we're rotating around. Now, if you think about it, sometimes I tell students, hey, think about if your eye's over here. So what happens as this little rectangle goes around there? And so we'll like that. Well, what happens is there is a hole that is there, and the hole is formed by this. So that's what we got, and so this is what we're going to get for this. And notice that I did draw my slice perpendicular to the axis of revolution, which means I can use the washer method. But notice this is not the disk method exactly. It is the washer method because there's actually 2 radii involved. So that is the picture. Okay, so now I did show you a picture now. So we have an outer radius, that is capital R of x is the square root of x, that is the outer radius, and lowercase r of x is x squared, that is the inner radius. Okay, well, you got a formula there, and we figured out, well, I kind of waved my hands, but it's not hard to figure out that those two curves intersect at 0 and 1, so we're integrating from 0 to 1. So what we're going to do is this is the general formula, is going to be pi on the outside. This is the integral from a to b, and this is r of x whole squared minus, this is capital R of x whole squared, that's the outer radius, minus lowercase r of x whole squared, and it is dx because that was the axis of revolution, and we drew perpendicular to that. So now we're going to substitute in, and we figured out from our picture what was the outer radius and what was the inner radius. So for capital R of x, we're going to substitute the square root of x, so we can substitute that in there. That is easy to do. And then here we get x squared, but x squared squared is going to be x to the 4th. So you see you're going to have pi. This is going to be the integral from 0 to 1. This is x minus, and then I said that was x to the 4th. And if you square the square root of x, you get x dx. So this is what you have to integrate. And again, I'm expecting you to do the calculation. Now there's going to be a pi in your answer. And by the way, that may be some of the reasons that that you guys think, I shouldn't say that you guys think, but that is one of the reasons that pi happens a lot is because, wow, it comes up in these kind of problems. Let's do the integral. If you integrate x, you add 1 to the exponent, divide by the new exponent, minus. Here you add 1 to the exponent, you divide by the new exponent, and then you plug in 0 and 1. Plugging in 0 is easy. That is just 0 in this case. If you plug in 1, you get 1/2 minus 1/5, which is 3 over 10. So it is 3 over 10 times pi. So it is 3 pi over 10. Okay, so what I'm going to do now is I'm going to pause for a count of 10 in case there are students who have questions about this example of the washer method.
I'm not sure if I heard it right, but is the capital R and lowercase r, were those given to us, or do we have to like find them through just looking at the graph?
You find them by looking at the graph. Now, the thing that you do know from the formula is that the capital R of x is the one that is the outer radius, and the other one is the inner radius. And I'm just going to go back to your picture. Yeah, so here's your picture. And so you can look at this, you see you're going around this. So the donut that you're getting, the outer radius is going to be this function, and the inner radius is going to be this function. But no, you have to figure that out from the graph. So I hope I answered that question. I start my count again.
I just want to make sure I'm tracking. So outer radius is going to be the top curve, and the inner radius is going to be kind of the bottom curve every time. If it's
well, no, and I'm sorry, I'm not trying to be mean with this answer. You got to look at the picture, because here we were drawing slices that were vertical, and there you talk about top and bottom. If you're drawing horizontal slices, you talk about right and left from yesterday. So you really got to look at the picture. You really got to think about the problem.
That makes sense.
And that's why I draw. Yeah. So you're okay. I mean, you understand my answer, yes?
Yeah, yes.
Excellent. Okay. Starting my count again. Okay, your questions are always welcome, but I got to 10 Mississippi, so we're going to move on. Okay. And by the way, the young student who asked that last question, this one is, and everybody knows what I'm erasing here. See, I'm not just going to give you the pictures, you have to come up with them, so I will save this yet again. We'll go back and we'll look at this. So here's another example. And again, if we were in a regular class and had regular time, I would just say, hey, you guys try this, and then we'll talk through it. So find the volume of the solid formed by revolving the region bounded by the graphs of y equal x squared plus 1, y equals 0, x equal 1, and x equals 0 and x equal 1 about the y-axis. Hey, we're going around the y-axis here. So you have to draw a picture of this, but that's what we need to find. And again, when you're doing the homeworks and things like that, you really should say, oh yeah, I have to draw these pictures because that's what I'm practicing to do. Okay, so we have that, and that's my example 4. Okay, so here we go then. Wow, and I need to go back here. And okay, so this curve right here is called y equals x squared plus 1. And so I'm going here, and this is y equal x squared plus 1 is this curve shown right here. Okay. And we're going around the y-axis, which means we're revolving it around this. Now, the only thing we've learned so far is either the disk or Washer method. Now, we're going to learn other things, but that's what we've learned so far. Tomorrow, we will learn about the cylindrical shell method. But what we're studying right now is the Washer method. So this gets to be a little bit involved because and so in the disk and Washer method, what that means is we always draw a slice perpendicular to the axis of revolution. So I'm drawing a slice perpendicular to the y-axis and a slice perpendicular to the y-axis. But look what happens. Down here, when y is, and by the way, when we draw this, we say, oh, this is a dy problem because I drew this slice. So when I'm going from y equals 0 to y equal 1, the function that's on the bottom is this x equals 0 function. And the function that's on the top is the x equal 1 function. So this part really, well, okay, so we got that, and that's actually just a rectangle, or actually that's just a square, I suppose. But things change after you go after 1. So you go from 1 up to 2 here. There, the function that is on the top still is x equal 1, but the function that is on the bottom is this thing. But I'm integrating dy. So if I'm integrating dy, what I have to do is I have to have these things be functions of y. Now down here, there's no problem because it's the function. It is 0 and it is 1. So those are easy calculations. Up here, the top one is 1, but the bottom one is this function. But this has to be a function of y. So I have to solve, and let me go back to the statement of the problem. So I have to solve this thing to make this a function of y. So I subtract 1 from both sides, and then I take the square root, and it is the positive square root. So you see, for y, for 1 less than or equal to y less than or equal to 2, what I have is that this lowercase r, and by the way, see, we're going around here, so if you're putting your eye somewhere, you might be looking up here, looking down at this, but this is going to have a hole in the donut. There's no hole down here. So we're going to have two integrals. So the first integral down here is going to have capital R equal 1 and lowercase r equal 0. And that's for y between 0 and 1. But for y between 1 and 2, we have capital R, the outer radius is still 1, but the inner radius now as a function of y is the square root of 1 minus y. And if you think about this, as you revolve this around here, you get something that looks like this with a hole in it. And I don't know, this could be, I don't know, but it could be something you would put a potted plant in or something. Okay, so we will continue then. Okay, so you see, there are two integrals we have to do. So these are the two integrals. So V, the volume, is going to be the first integral, and then the second integral. Okay, so here's the first integral, and the first integral is that doing really that square. You could actually do this in your head, I suppose, but this is going to be pi, and then I integrate from 0 to 1. And the outer radius for that lower block was 1. So that is 1 squared minus 0 squared. That's just 1 dy. But then in the top, it is a washer, so it is pi. Now this integral now is y. It's going from 1 to 2. And so this is the outer radius, which is 1 squared minus, and this is minus the whole of lowercase r whole squared, and then that is dy. Okay, so we continue doing this calculation. That's 1. You integrate 1, and you substitute things in. This is just going to be pi. It was a rectangle. Okay, so it's just going to be pi. It's pi square units, or actually pi cube units when you plug, because you've integrated with the dy. Now here you integrate 2. You add 1 to the x. This is y, 2 times y to the 0. And so you add 1 to the exponent divided by the new exponent. This is 2y minus this minus sign is that minus sign. And this is y to the 1. I add 1 to the exponent divided by the new exponent. And then I plug in the numbers, and I'm integrating that. And again, a serious student, when they're going through the notes, they would say, oh, I want to practice this calculation. That's going to be pi. This is going to be pi times all of this business. It looks like I have 4 minus 4, so that drops out. So this is pi over 2. This is pi plus pi over 2, and that is 3 pi over 2. Okay, now I think what I'm going to do is I'm going to pause for a count of 10 Mississippi, in case there's questions on this example that we just did.
Since we don't, all right, I might be thinking about this wrong. It doesn't seem like we need calculus to do the bottom volume. The bottom volume is just
you don't need calculus to do the bottom. That's what I was trying to say. Is this is just a rectangle? So, and in fact, it's a square. So that, but you have to remember this. It's a square, but it's times pi.
Yeah.
Okay, so you have to remember the pi. But yeah, I mean, in truth, I would have done that one in my head if I were doing the problem, and I wouldn't have made two integrals. But I'm just showing you how it works with that. So yes, you're correct. So I'm thinking I answered that question, and so I will go back to my my count again. Okay, your questions are always welcome, but I hit 10 Mississippi, so that's we had opportunities to ask questions. And you certainly can ask questions other times. So that is all good. Okay, so let's go to this. Now, this is a real world problem, example 5. So we will talk a bit about this, and this example is a little bit more involved. So a manufacturer drills a hole through the center of a metal sphere of radius 5 inches. And again, if I were to ask you this problem, I wouldn't give you the picture. I would just say, yeah, read it and figure out what it is. Okay, so I will save that, and I'll do the same for your sister class. Okay, the internal hole has a radius of 3 inches. What's the volume of the resulting metal ring? I actually have a pretty nice LSA that deals with a problem a little bit like this. It's a ring problem. I actually like it, and I need to go and dig that up. But Dale, there may be another one coming sometime soon. But anyway, that's what we have. So you have to think about, okay, so what's going on with this? Here's what's going on with this, and I will make this into a bigger picture. So this is what's going on. Okay, now if you look at this, this is a sphere, okay, but what you're cutting out is and actually you should think about this, you're cutting out a cylinder, okay, because here's a circle here. It's going to be a circle at the other end, but then this has a depth or something. Okay, so looking at this picture then, the sphere, and by the way, you get to pick a coordinate system. Nobody said that, you know, what your coordinate system is, and that's actually what happens in a lot of real world problems. You, as the analyst, get to pick your coordinate system. And sometimes it requires experience, and we'll talk about that. That's a little bit of tradecraft. But this is what I'm doing is I'm going to say, oh, I'm just going to take 0, 0 down here, and I'm going to pretend that we're going around the x-axis. So you see, this is my choice to do it this way. But in fact, in math, what we would say is, oh, without loss of generality, we could assume we're doing it like this. So that is good. So now we've picked a coordinate system, which is good. Now but then we have to say, well, okay, but if this is the xy plane, what's really going on? Well, you see, we're rotating around the x-axis, so this is here. But what are we really rotating around? Well, you see, if we were just rotating the circle in the plane, you see x squared plus y squared equal 5 squared is the equation of the circle. It is an equation of the circle. And so this top part, that's where the radius is 5. But you see, it really depends. I mean, the radius is 5, but it changes as you go along, because we're rotating the things that are between 3 and 5. So you see, if you take 3, you get this is y equal 3. So that means this r of x is 3 down here, and the big R is 5. But the equation of that, you see, that changes as it goes along the x-axis. So this is the equation of the circle. So this is capital R of x is equal to the square root of that, because this was a sphere. So this is x squared plus y squared, actually plus z squared is equal to that. Okay, so that is what we got. So you see, this is going to be rotating the outer surface, which is the square root of 25 minus x squared. But then your inner radius is r of x equal 3. So this is the picture that we have for this thing. Okay, so now we say, well, so clearly it is a washer. And so you can imagine the ring to be generated by a segment of the circle whose equation is x squared plus y squared equal 25, as shown in the picture I just showed you. Because the radius of the hole is 3 inches, you can let y equal 3 and solve this equation, x squared plus y squared equal 25. Now you see, if you take y to be 3, you're putting a 9 there, which means that this is x squared is equal to 16. So x is going to be plus or minus 4. Okay, so those are your limits of integration. And the inner and outer radii are the inner radii of the radius of this is r of x is equal to 3. The outer radius is capital R of x is equal to the square root of 25 minus x squared. And our formula is going to be volume is equal to pi, the integral from the limits. This is the outer radius. And this is going back to the question the student asked, that the outer radius, it really depends on the problem, but you get it from the problem. The outer radius whole squared minus the inner radius whole squared. But now we're going to substitute in. So there's pi is pi. We figured out that the limits were -4 and 4, so that was good to go. This was capital R of x whole squared minus, and this was lowercase r of x whole squared dx. Okay, and then you square this, you get 25 minus x squared, and then this is -9. That makes it 16 minus x squared, and you did this from -4 to 4. When you enter, the pi just sits out there, but 16, when you integrate that, you raise, it says 16x to the 0 power. You add 1 to the exponent, you divide by the new exponent, so that is 16x. This minus sign is that minus sign. This is x squared. You add 1 to the exponent, and you divide by the new exponent. And we plug in numbers, and you are going to have to plug in numbers, and you're plugging in numbers without calculators. But you will get 256 over 3 for this part, and then it is times pi. So the answer to this is 256 pi over 3. Now I'm going to pause for a count of 10 in case people want to ask questions about this problem. Well, your questions are always welcome, but I hit 10 Mississippi, so we'll move on. Okay, and now we come to the final topic, and we have some time left. I think this will all work. Now, last time I talked about looking at an integral as being an accumulation process, and you can go back and look at the notes and see that we did talk about that, but we're going to be doing this now. But now we're talking about solids with a known cross section. So this is a class of problems that's a little bit different than what we talked before. And so with the disk method, you can find the volume of a solid having a circular cross section, whose circular cross section was the area is equal to pi r squared. Okay, and we talked about that, and that can be generalized, but this method can be generalized to solids of any shape. What we're doing is we're doing the integrals as an accumulation of the cross-sectional areas, as long as you know a formula for the area of an arbitrary cross section. And some common cross sections are squares, because you know the area of a square is x squared. A rectangle, it's x times y. Formulas for triangles, semicircles, and trapezoids, and ... We could do all kinds of things there. Okay, so here are the formulas that you want to keep in mind for this. So suppose your cross sections are always of the form a of x. So for cross sections of, these are called uniform and known cross sections, a of x, and this is taken perpendicular to the x-axis. And the reason we're doing perpendicular to the x-axis, the area of this, is that this chapter is about the disk and washer methods, where we're always taking the slices perpendicular to the axis. But later on it's going to be different, but this is what we're doing here. So for areas, do that. What we're really going to say is, oh, the volume is, well, here's the area of x. And you see that's going to give me square meters, but then I take it times dx, that's going to be meters cubed, and I just add them up. This is the accumulation of areas. And similarly, if I'm doing cross sections of a of y taken perpendicular to the y-axis, now there's perpendicular y-axis, which means you're doing that, you're accumulating, but this is going to be the integral of the cross section area a of y dy. And we're supposed to be looking at a picture, so I will show you a picture. Okay, so here is a picture, so here we're talking about cross sections, and you see when you're in 3 dimensions, everybody, you've got an x-axis that's going this way, you've got a y-axis that's going this way, and you actually got a z-axis going up and down. But what we're saying is that here we have a cross-section perpendicular to the x-axis. So here is a geometrical figure that is perpendicular to the x-axis. So you see, every time you change x, you get another geometry figure that is like this. Okay, so you're integrating from, you're integrating x. So we have a picture like that. But here, we could say, and it looks to me like this is a square. I'm trying to look. I can't tell exactly for sure what this geometrical figure is, because this one is curving. But anyway, you could say, oh, here is it is a square where cross sections are perpendicular to the y-axis. So you just say, oh, I'm just stacking a whole bunch of squares, but here I'm integrating dy. Okay, so now we're going to do a problem. This is not a particularly easy problem, but we're going to. I'm confident I can finish this. And I'll pause for questions at the end. But anyway, now in a problem like this, they have to tell you something. And here what they're telling you is the cross sections that are perpendicular to the x-axis are equilateral triangles. Okay, and so that's what I'm saying. And you see, when I tell you you got equilateral triangles, I don't have to say shown in a figure, because I'm not going to do that. I will say that again for your sister class. Okay, so we're trying to find the cross. So we know that we're building a thing, and the cross sections perpendicular to the x-axis are equilateral triangles. So find the volume of the solid. Now they tell us that the base of the solid is the region bounded by the lines. This is one of the lines, and this is another line, and x equals 0. You see, they're really giving you a thing to make a triangle out of this. Now let's look at a picture, because you have to read this and think about it, and there really is thinking involved, but you draw a picture. So you see, here's what we're getting. Okay, so here is one of those lines. This is y equals g of x, which is down here. Here's the other line, which is f of x is equal to 1 minus x over 2. Now you have to graph those, and here's a picture of those. But you see, we're building equilateral triangles. So we're perpendicular to the x-axis. So this thing, this slice that we're drawing here, everybody, is this slice is perpendicular to that axis, because that's what the problem told us. But this is the base of an equilateral triangle. So the height of this triangle, so there's the base right there. The height of this triangle is the height of the equilateral triangle that we get here. So this is a length of a side. Now here you got an equilateral triangle that's of that size. When you go here, you got a bigger equilateral triangle. Okay, but we have a formula for this. So all we have to do is figure out what is the area, depending on x, of the equilateral triangle that is here. So we have to use some geometry. Looks like I pasted the same. Did I go backwards? I pasted that twice. That's no good. Anyway, we'll go here. Okay, so what you have to do is you have to say, well, figure out what the area of the triangle is. So the base of the triangle is the top function minus the bottom function. You see, we know this is the top function minus the bottom function. So that tells us what is the length of the side. Okay, so this is the top function minus the whole of the bottom function. You have to do that, but the length of the base is this. So then you have to know what is the area of an equilateral triangle. And I am watching my time for you, and so we may have to begin our next period, fielding questions on this, and I'm happy to do this. I could go over time today, but I'm choosing not to. So you know what a side is, and if you know what a side is, you should be able to figure out what is the area of an equilateral triangle. And I'll show you this next time if you want. This is the square root of 3 over 2, and this is because an equilateral triangle the angles are all 60 degrees. And that's one of your special 30, 60, 90 right triangles. So you see, this is something you should know from your geometry. So this is the area. So that means the area as a function of x is, here's the base squared, and you got that constant. So that is area of a cross section. Now x ranges from 0 to 2. I think maybe they told us that in the problem. Let's see, I need to go back. Actually, we have to calculate that too. But x ranges from 0 to 2, so the volume is, we integrate from 0 to 2. This is a of x. Now I have to square this, and I guess I could do a u substitution in this particular case, but I have to calculate this anyway. So you add 1 to the exponent divided by the new exponent, but when you change the variable, you get a minus sign, so you have to do all of this calculation, and you get the answer to this problem is 2 square root of 3 over 3. Okay, now, by the way, that worked out just, well, I actually had one more example that I was going to do, and I'm probably not going to do that. I'm just going to declare us finished there. So that is where we're kind of finishing. I have a minute, so I'm going to count to 5, Mississippi, in case anybody wants to ask questions. And I am actually, we ran out of that time too. So thank you, Thomas, for your help. I am going back to, I guess I'm going to save this once again. I'm going to go back to Blackboard, and I guess I need to, should stop sharing. The thing I'm really going to do, I'm going back to Blackboard, and I am stopping the